having said that, it's my pleasure to introduce Jakub Witaszek, who will talk on mixed characteristic minimal model program.
Hello, everyone. Is the microphone working well? Wonderful. Okay, so I'd like to start my talk by saying it's great to see all the familiar faces in the audience and all the old friends I haven't seen for many years. I would also like to thank the organizers for an opportunity to talk today. It is a great honor. Okay, so the goal of my talk today is to conclude our small lecture series with Carl Schweid and Kevin Tucker on these recent developments in mixed characteristic commutative algebra and birational geometry. And in this last talk, I'm going to tell you how these recent developments led to some new results in the mixed characteristic minimal model program. And so my talk is going to consist of 4 parts. First, I'm going to do a very brief review of the minimal model program over complex numbers. Then I'm going to move to describing the state of the arithmetic minimal model program. Next, I will move to the key components of the proof, and I'll conclude the talk with a series of applications. Okay, so without further ado, let's start with the review of the minimal model program. The curtain's open. So the goal of the minimal model program is to decompose every projective variety into basic building blocks up to birational equivalence. These basic building blocks are Fano varieties. This is when omega x is anti-ample. Calabi-Yau varieties, when omega x is numerically trivial, and strictly general type, when omega x is ample. Intuitively, this corresponds to positive, zero, and negative curvature. Now, we're going to achieve our goal by the way of the following basic operations, f going from x to y. And because we want them to be as simple as possible, we're always going to assume that the relative Picard rank is 1. Moreover, our goal is to make the canonical divisor as positive as possible. And so we will assume that the canonical divisor is always anti-ample over the target of a basic operation. And so we have 3 basic operations. We have divisorial contractions. These are birational maps contracting a divisor. We have Mori fiber spaces, also known as Fano fibration. For these, the dimension of the target is smaller than the dimension of the source. And because the canonical divisor is anti-ample over Y, a general fiber must be Fano. And finally, we have a flipping contraction. This is birational, but small. The dimension of the exceptional locus, the codimension of the exceptional locus, is at least 2. Now, because flipping contractions introduce pretty bad singularities. We always follow a flipping contraction. We always follow a flipping contraction by a flip. So what is a flip? Well, a flip is a rational map going from x to x dagger. Please look at the diagram here. And x dagger also admits a small relative Picard rank 1 map to the base y, but now the canonical divisor is ample over the base. Intuitively, what we do, we take a codimension greater or equal than 2 subvariety, we remove it, and we put something back in its place to increase the total positivity of the canonical divisor. So these are our 3 basic operations. So now let's move to the statement of the minimal model program. And I will assume that x is a regular projective variety over an excellent scheme S. And we may assume that x has mild singularities. In the context of the minimal model program, that means that x has KLT singularities. And a simplified version of the MMP conjecture predicts that there exists a sequence of divisorial contractions and flips. Here denoted, their composition is denoted that x going to y is a rational map, such that y is a minimal model, the canonical divisor is Neff, or y admits a Fano fibration. Now, the most important part of the minimal model program conjecture over complex numbers is now a theorem, thanks to the breakthrough work of Birkar, Kashini, Haken, and McKernan, which is arguably one of the greatest achievements in algebraic geometry in the recent decades. Now, the minimal model program conjecture is complemented by the abundance conjecture. Before I state the abundance conjecture, let's recall that a line bundle L is called semi-ample if some power of it is base 0.3. Now, the abundance conjecture says that if the canonical divisor is Neff, then it is semi-ample. In particular, by looking at the associate linear system, we get a fibration fx to z, whose fibers or general fibers are Calabi-Yau, and the base is expected to be of log strictly general type. If we combine the minimal model program conjecture with abundance conjecture, we get the following. Let's start with our variety. Let's run the minimal model program until we reach a Mori fiber space. Then repeat the MMP for the base Z of a Mori fiber space and keep going through multiple Mori fiber spaces until we reach a minimal model. Then we are going to apply abundance conjecture and construct a Calabi-Yau fibration whose target should be kind of like of strictly general type. And this way, we decompose our variety into these three basic blocks I mentioned in the beginning. Unfortunately, abundance conjectures open beyond dimension 3 over complex numbers. So that's a very brief recap of the very foundations of the minimal model program. But before I move on to mixed characteristic, I want to give one more slide. And that's about semi-stable minimal model programs. And these are very important applications, and they're going to show up later in my talk. So let's start with the minimal model program over singularities. So let's X be a KLT singularity. In this picture here, this is a quadric. And let Fy to X be a log resolution of singularities, with E denoting the exceptional locus. And then what you can try doing is running the logarithmic minimal model program. So whose goal is to make Ky plus E to be as positive as possible. And we expect this minimal model program to terminate with the singularity X itself, which is known in very many cases. So this sounds very technical, but the slogan is very simple. Every resolution of a KLT singularity splits. It can be highly complicated, but it splits again into basic blocks, just flips and just contractions of single Fano varieties. And so every time you like to study singularities, you can use MMP to simplify your problem. For example, assume you want to prove property P for a singularity. Right? You're going to start with a resolution, which should satisfy property P. And you need to show that this property is preserved by flips and by contractions of Fano varieties. If you can do that, then you're going to run the MMP and descend the property P over and over through the minimal model program until you reach the singularity X. And this shows that X satisfies property P. The second type of MMP that is very useful is the minimal model program for models. So let's, in here, we are having our elliptic curve, and let's degenerate this elliptic curve to a union of 3 lines. Now, that will be pretty boring, so let's pick a point on this special fiber. Let's pick this point and blow it up. This way, we get a new degeneration, where the special fiber consists of 4 lines. Okay, so let's call this model X. And for simplicity, assume X is regular. It's defined over dVr r or a curve. And we are going to assume again for simplicity that the reduced special fiber E is simple normal crossing. Then let's run the logarithmic minimal model program again. And this MMP is going to simplify our variety. It's going to remove a lot of redundant data. It's going to give us the most efficient and the best model we can hope for. Right? In particular, in this example, what this MMP is going to do is going to contract this additional fourth curve. This additional line was clearly unnecessary and recover the original degeneration, which is maybe the best possible degeneration of a given deformation you can consider. Okay, so I'm going to now move to the arithmetic situation, but let me point out that, whatever research you do, I really I find this idea very enticing, that every time you encounter a singularity, every time you encounter a model, you can ask yourself, well, can I apply these ideas to help me with my problem, right? I have the deformation, maybe the MMP can help me to construct a better deformation that is more approachable to my problem, or maybe I have singularities and they look very complicated, but the MMP can simplify them. We are going to see a lot of such applications in the arithmetic part of my talk. Okay, so now we move on to the arithmetic minimal model program. And I really should start my talk by saying, why would we even care about studying the arithmetic minimal model program? And to answer this question, there are many ways you could answer this question. But let me give you one example. So suppose you walk on the street and a friend of yours walks over and hands you a system of polynomial equations with integer coefficients and asks you for help. They want to find all integer solutions. Now, one example of such would be Fermat's last theorem. And as much as I would like it, the MMP is not going to help you with the Fermat's last theorem. However, it can still help you to decompose your problem into a series of more manageable ones. Okay, so let's kind of turn on our imagination and now imagine this system of polynomial equations to be a mixed characteristic variety. Let's run the minimal model program. It will decompose our variety into these three building blocks: Fano, Calabi-Yau, and general type. Now, let's use some arithmetic to find the solutions, the number of integer solutions for each building block. And now let's sum them together. What you get is the answer to your problem, the number of integer solutions to your original system of equations. Okay, and so in some situations, that's kind of a performance can help you to solve your problem. But here we go to the main and the key part. This is the block here. This is fundamental, is that when you run this MMP, you definitely want all your maps to be defined by integer polynomials. The moment you use fractions, the moment you use 1/5, 1/7, or 1/11, the answer you're going to get may be vastly wrong. And it's something that feels very unnatural. If you're a geometer, you kind of you don't even think about it. In all your formulas, you're going to use fractions left and right. But you can't do this in mixed characteristic. A similar framework will apply to positive characteristic. So instead of solving Diophantine integer equations, we are going to solve congruences modulo p, and we can apply MMP to maybe decompose our system to more manageable ones, and some solutions get your answer. So hopefully I motivated you just a little bit about how the mixed characteristic minimal model program can be useful. And so let's start with a bit of a history. And so let's start with the positive characteristic minimal model program. And so I should start with three things. Firstly, of course, I should start with a Bombieri-Mumford's result, the extension of Kodaira-Enriquez classification of surfaces to positive characteristic. Then we have a very important result by Professor Kawamata on the semi-stable minimal model programs, as talked about on previous slides, for threefolds in positive and mixed characteristic when the characteristic P is greater than 3. And finally, we have much newer results. This is the work of Tanaka on the modern minimal model program, who developed an MMP for surface in almost full generality. The key result for us, and the starting point of the whole discussion today, is the breakthrough result of Christopher Haken and Chen-Yang Xu, who proved the minimal model program conjecture for threefolds in characteristic P greater than 5. Now, there are certain restrictions there, and so in almost full generality, we know the minimal model program in characteristic P greater than 5, thanks to the work of Kashini, Tanaka, Xu, Birkar-Waldron, Das-Waldron, and others, and in the case of P equal to exactly 5, thanks to the work of Christopher Haken and myself. Moreover, there's been significant progress on the abundance conjecture. Chen-Yang Xu and Lei Jiang proved the non-vanishing part of the abundance conjecture, and there's been important progress for partial abundance by Jiang Xu. Okay, so now we reach the two main statements of today's talk. So this is a theorem by Takamatsu Yoshikawa and a theorem by Bat, Ma, Patakfalvi, Shui, Tucker, Waldron, and myself, proved independently. And so Takamatsu Yoshikawa established this semi-stable minimal model program for mixed characteristic threefolds in every characteristic, vastly expanding the work of Professor Kawamata. And our 7-author collaboration extended the work of Christopher Haken and Chen-Yang Xu to mixed characteristic. And so we established the minimal model program for mixed characteristic threefolds when the residue characteristics are 0 or greater than 5. In other words, we need 1/2, 1/3, and 1/5 in our rings. Another way to think about it is that when we run our MMP, we can't really use integer polynomials. We still need to use 1/2, 1/3, and 1/5 in our formulas and products thereof, but no other fractions. Okay, so these are the two main results, and I'd like to tell you a little bit what kind of components are used in their proofs. But before moving on, let me make the side remark. And so, Bargav, Linchuan, Joel, Carl, Kevin, Joe, and myself, we've been working on many papers, articles. You've heard about some of our results in the previous lecture series. but I've been always very, very disappointed by the acronyms for our papers. So it reads BMP STWW. It's extremely boring. And so I was very disappointed about it until a friend of mine decided to ask ChatGPT, what does BMP STWW stand for? And the response of ChatGPT was, starting from the first surname, basic math problems, sometimes test willing warriors. And so another way to think about our lecture series is that for the last 3 weeks, Carl, Kevin, Joe, and I are trying to tell you how some basic math problems sometimes tested us willing warriors. And what makes me particularly happy about ChatGPT response is that according to ChatGPT, I'm the warrior of the team. Okay, so putting that comment aside, let me tell you a little bit about some further developments that happened after these results were announced. And so let me tell you about 3 such results. So first, we have the result by Xie Shui, who extended our mixed characteristic minimal model program to characteristic 5, building on the previous work in positive characteristic by Christopher and myself. And so in particular, now we know the mixed characteristic MMP for 3-folds when the residual characteristics are 0 or greater than 3. So we only need to use 1/2 and 1/3 in our formulas. We're almost there. Just these 2 fractions are causing troubles. 1/5 is not necessary. Next, despite the fact the abundance conjecture is still open in positive characteristic, the abundance in mixed characteristic has already been proven. This is the work of Bernasconi, Brivio, and Stigand. They established the abundance, again, characteristics greater than 5 in mixed characteristic. And finally, let me mention the work of Christopher Haken and myself, with a very important contribution by Xie Shui to the termination, to the effective case and the Mori fiber spaces. And so what we can now do is also a semi-stable minimal model program for mixed characteristic 4-folds when residual characteristics are 0 or greater than 5. Alas, as you've already heard from Carl's talk, resolution of singularities are only true up to dimension 3. So they're not known in dimension 4. And for this reason, for some of our results, we need to assume resolutions. However, I see a lot of, very eager and smart young people in this audience. And so I'm very hopeful that some of them could try to replace resolutions by alterations. We did not succeed, but I'm very hopeful that it can be done. So I'll be extremely excited if someone found a way to do it. Okay, so that's more or less the state of the art currently. And so what I would like to tell you now is what kind of components went into the proofs of these statements. And so these are the key components of the proof, and they're going to be, I'm going to talk about them by ways of answering the following 2 questions. So these are the key questions. They are the key questions for us: how to construct flips, and the idea is to lift sections to show finite generation, and how to construct contractions. Here, the idea is to show semi-ampleness of line bundles. Okay, so let's start with the harder one, the construction of flips. To this end, I need to do a very brief recap of previous lectures. Because again, we remembered our goal for now is construct flips. And so I need to review 4 things. The first thing is the definition of a splinter. We're going to say that X is a splinter if for every finite cover Fy to X, the pullback map from OX to OY splits in the category of OX modules. The second thing is a low dimensional input. Is exactly the thing that prevents us to establish the minimal model program at this point in higher dimensions. And so the low dimensional input we are going to use is the fact that KLT surface singularities in mixed characteristics 0, p greater than 5 are all splinters. This result, unfortunately, is false in higher dimensions, so there's no such similar bands for 3-fold singularities and higher, that kind of universal bands starting from which the KLT surface singularities are splinters. So there is something special. There's an explicit calculation you go through to check that these KLT surface singularities are splinters, and already Kevin mentioned that in his talk. Very briefly, one way to prove it is to use the framework I told you about earlier. We have a singularity. We are trying to prove a property of a singularity. What we do, we take a resolution, and then we start contracting curves. We run the minimal model program, and you show that the property of being a splinter is preserved by all the contractions you encounter. And that eventually tells you that the singularity you get are splinters. And the way you show that contractions preserve the splinter property is via a framework of the inversion of a junction, the global version of inversion of a junction that Kevin mentioned already in his talk. Now that these are curved, oh, there's something very important I should say. Let's go back. So there's a certain misunderstanding here. What did we really prove? And so what do I mean by a threefold? By a threefold, I mean a variety of global, of absolute dimension 3. It's not a relative dimension. In particular, the way to think about these are degenerations, arithmetic degenerations of surfaces over ZP or Z. But we are not assuming anything about, in the second result, about the special fiber. It could be vastly horrible and singular and non-normal special fiber. But really, the picture you should have in mind is arithmetic degenerations of surfaces, arithmetic models of surfaces. Okay, in particular, when you extract curves, you're going to see that these extracted curves live in positive characteristic. And so you can try using positive characteristic method and the framework or inversion of a junction to show the splinter property. Okay, now we move to two more components. And that's the Bad's breakthrough theorem, of which I'm a big fan of. And so Bargov's result says the following. We're going to start with an excellent local domain of mixed characteristic 0, p greater than 0. Then Bargov tells us that R plus is cohomologically Cohen-Macaulay. Okay, so already Kevin talked about it. And so one way to think about it is that the local cohomology for dimensions smaller, for I smaller than dimension of R, are all vanishing. Oh, R plus, oh my God, yes, there should be HIM R plus there. Yes. Replace R by R plus, sorry about this. Another way to think about it is that if you p-adically complete R plus, it's gonna be big Cohen-Macaulay, as already discussed in Kevin's and Carl's talk. So satisfy the usual regular sequence condition. Now, it might not sound it might sound a little bit technical, but it's really, in some way, I think of it as a result that revolutionized a big part of commutative algebra and birational geometry in mixed characteristics. Has tons of applications and really provides a much better framework to understand all these recent developments in commutative algebra, like, for example, the direct summand conjecture. What is particularly exciting about these results for birational geometers is when we apply these results to an R, is a cone over a variety, right? The most simple singularities are cones over varieties with respect to some ample line bundle L or a very ample. That you might remember that the local cohomology of a cone is going to be a direct sum of cohomologies of twists of that line bundle. And so Bad's breakthrough result puts that into the framework of Kodaira vanishing. And so what it really implies is that for L being an ample line bundle on a d-dimensional X, projective over a mixed characteristic BVR, I will assume for simplicity that X is regular, which allows me to make a slightly more simplified statement than in the previous talks. Then the L inverse, the pullback of L inverse on X plus. So I'm looking at X plus, that's the limit of all finite extensions. The cone of which should be thought of as R plus. It's a bit more complicated, but let's assume that. Then we pull back this L inverse there, and the previous statement about local cohomology tells us that this cohomology vanishes. Now, this looks very complicated because X plus is non-Noetherian, but this can be reformulated in a much simpler way. So what it does really say is that equivalently, if we look at the ith cohomology of L inverse on X, which in characteristic 0 is supposed to vanish by Kodaira vanishing, but again, we know vanishing theorems break in positive and mixed characteristic. Nevertheless, Bargov results tell us we can take a cohomology class in HIXL inverse, and you can find a finite cover that if we pull back our cohomology classes by this finite cover, they're all going to be killed. So we can kill cohomology classes that should vanish by Kodaira vanishing by some additional finite covers. Okay, so these are the 4 things I wanted to review. I mentioned 5. So the 5th is the set of stable sections B0 that Carl told us about, but I will postpone that until the next slide. Maybe this is a good point to answer another question that I've been asked many times: is how did our 7-author collaboration started? It's quite a lot of people, and it boils down to an MSRI program in Berkeley many years ago. So it was after Andre proved the direct summand conjecture, again revolutionizing commutative algebra, and a lot of cool things came out of that proof. You had the construction of these big Macaulay algebras. We got certain vanishing that came together with that. And it looks like a perfect time to try to attack the MMP. And many people, there are different groups in our 7 collaboration. We're all kind of slowly converging towards that goal from different angles. And it seems like a perfect opportunity to kind of start a joint collaboration. And so this preceded Bath's breakthrough theorem. And so at that time, we tried using this big Macaulay algebras to solve our problem, but it was hard. We were making progress, but a lot of things that you would expect to be easy were very hard when you work with big Macaulay algebras. And then Barga's results came along, and it simplified so many things. Like a lot of things that were hard or almost impossible in our setting became easy. And then with quite a bit of work, we managed to use that result to push our theorem. Okay, so that's a little bit of history. So let's now move to the harder part. And so let's construct flips. Okay, so the goal for now is to construct the flip x dagger of x. Of course, I will simplify things a lot. This takes quite a lot of time to explain how flips can be constructed, but I kind of want to convey some key basic ideas that kind of gives you some kind of that may be applicable in other contexts. Okay, so let's look at the diagram on the right. I'm starting with a flipping contraction, x to z, denoted f. And my goal is to construct this flip, this x dagger over z. Recall in the flip is a small map over z, but the canonical divisor on the flip is now relatively ample. I will assume for simplicity that the singularities of x are isolated. Things work in general, but this is going to make my life a bit easier. So the first thing you've observed, so that's the first box, is that the construction of flips is a local property over z. So we may assume that z is affine. Now I'm going to look at the following object, R. I'm going to look at all the sections of multiples of the canonical divisor, positive multiples, non-negative multiples. I'm going to take all the global sections. And now this is in fact a ring, because sections can be multiplied. So I have this ring R. And a very basic result in birational geometry says that if this ring is finitely generated, then the projectivization of that ring over z, over the base of the flipping contraction z, exactly gives us the flip. And so our problem is simplified to kind of a much more concrete one. Our goal is to show that this very basic ring is finitely generated. But of course, showing finite generation is not always easy. So the next step is to use another idea that is kind of omnipresent in birational geometry. And this idea is we always lift from lower dimensional varieties. So we always, like in a lot of proofs in birational geometry, we always want to lift the results from lower dimensional varieties. And so we need to pick some nice divisor D from which we can lift sections. And the one I'm going to pick is an anti-ample divisor D. Unfortunately, there is no Bertini theorem for anti-ample divisors. So such an anti-ample divisor could have absolutely horrific singularities. However, we have another trick in our sleeves, and that's so-called reduction to PL flips. So there are certain frameworks in birational geometry that allow us to reduce. So maybe even though D itself has bad singularities, we have a way to reduce the problem to a situation in which D has indeed mild singularities. So in this context, we may assume that we have D with KLT singularities. Now, D is anti-ample. I'm going to set A to be minus D. And so A is relatively ample. Okay, so let's look at the second line of the second box. And let's calculate the canonical divisor of D by a junction formula. That's Kx plus D restricted to D. Now, Kx is anti-ample by definition of a flipping construction. And D is anti-ample by construction. So their sum is anti-ample. And we get that D is a relative final variety. And this is when the low dimensional input comes in. So I told you it was about KLT singularities, but we need something slightly stronger. is the fact that these two-dimensional Fano, relative Fano varieties, in characteristic p greater than 5, these are all splinters. This is some special arithmetic property that is true in these low dimensions, again, breaks to some extent in higher dimensions. So that's our low dimensional input. Again, we are really using here that this D is a surface to perform the calculations. So we go to box 3. So now we need to use one more simplification. And so the last thing one needs to check in order to show this finite generation is that the map from the canonical ring, or the sections of MKX, restricted to D, this map is surjective on global sections. So we need to show that surjectivity of sections. Again, in practice, things are a little bit more complicated. I like to, I hope experts forgive me to making a few simplifications there and there. But the idea is we want to lift sections. And then again, the general statements by rational geometry tell us that if you lift this section, you can show finite generation of R. The idea is briefly is that D is lower dimensional, then you're going to show finite generation at the level of D. You're going to lift all these sections of X. You're going to have so many sections of R that it's good enough to check finite generation. If you have a lot of sections, it's much easier to show finite generation. Okay, so let's start by checking this for M equal to 1. Okay, now it'd be useful to denote something, but let's look at the first row in this big diagram from M equals to 1. We see there here Kx plus D plus A. But remember, A is minus D. So what I really wrote is just I wrote Kx in a very, very complicated way. Right? Kx plus D plus A is just Kx. The right-hand side, the H0, is the restriction of Kx to D. Or equivalently, by adjunction formula, if you restrict Kx plus D plus A to D, again, I'm, here and there, I'm hiding the fact and assuming that D has isolated singularities for simplicity. If you restrict Kx plus D plus A to D, you're going to get Kd plus A restricted to D. And we look at the map on global sections. And in characteristic 0, this map is always surjective. Why? Because the next term is Kodaira vanishing, is H1 of the canonical sheaf shifted by an ample divisor, which is always 0 by Kodaira vanishing. So these kind of maps on H0 are always surjective in characteristic 0. Okay, so we have a problem. We need the surjectivity, but we do not have vanishing theorems. And this is where this B0 comes along. The B0 that Carl told us about. So recall that B0 is a subset of special sections of H0. These are the sections that behave as if vanishing theorems hold for them. They behave as sections in characteristic 0. And now we have the bottom row of this diagram is the same as the top row, but we replace H0 by B0. And we have a map from Kx plus D plus A to Kd plus A restricted to D. Now, by Bargaff's result and by what Carl explained to us in his first lecture, this map on B0 is always surjective, as you would expect on H0 and characteristic 0. So the lower bottom map is surjective, but this is still not enough to lift it to surjectivity on H0. We need one more component. But remember, we knew that D is a relative splinter. And this allows us to look at the rightmost vertical arrow and tells us that the rightmost vertical arrow is an equality. Again, Carl told us that H0 of D and B0 of D are always the same for splinters. So the bottom arrow, always true. The right arrow is where the low dimensional input comes in, the splinter property. If we combine these two conditions, we immediately see that the top arrow is surjective. Again, combining these two properties, we get that the top arrow is surjective, and we conclude the proof of surjectivity for M equals to 1. Now we need to prove the surjectivity for higher M. And of course, that's much more complicated. And in all of this framework, we are really following the following the ideas established by Christopher Haken and Chen-Yang Xu in positive characteristic. In particular, for higher M, you need to do much more work. And following Christopher's and Chen-Yang's idea, which in turn are build upon ideas of Shakurov, as explained in Alessio's Corti book on flips. So I really have no time to tell you what you do for higher M, but the idea in the end boils down to the same. You want to lift sections of H0. You can do it on B0, and you need to use some lower dimensional input. You need to use some lower dimensional input to say that the liftability on B0 lifts to the liftability on H0. As always, use B0 and use lower dimensional input and lift sections. That's kind of the key idea here, that you're hammering over and over and over and over again in various settings. Okay, so I know that was quite of a lot, but I hope that the key ideas came through in this construction and gave you some idea of how all these recent developments and how what Carl and Kevin talked about in the previous lecture fits into the framework of the minimal model program and the construction of flips. So now let's look at the second type of a problem, and that's the construction of contractions. And so let L be a line bundle on X. Let's define the exceptional locus to be the union over all closed subvarieties Z, such that the restriction of L to Z is not big. Now, Kill's theorem, the famous Kill's theorem, tells us the following: if X is projective in characteristic P greater than 0, then L is semi-ample if and only if L restricted to the exceptional locus is semi-ample. Hopefully, you can see how useful this theorem is, because it allows us to reduce our problem often to a lower dimensional one. If you're lucky, you may even try to running some form of an induction and decrease dimension further and further ahead. And so this result was used. Yes, I'm sorry about yes. I need to assume in the first. It was very false otherwise. I should assume in the first line that L is an F-line bundle. Thank you. And so this result was used by Chen-Yang Xu and Christopher Haken in their construction of contractions in positive characteristic MNP. Interestingly, this result is false in characteristic 0. So this kind of like a very interesting phenomenon is like most of the things are much worse in characteristic P, like vanishing breaks and so on and so forth. But this is one advantage we have. We have Kill's theorem that is false in characteristic 0 and allows us to prove many things in a much simpler way. And sometimes even allow us to show that certain line bundles are semi-ample, even though they are not in characteristic 0. But since this result is false in characteristic 0, it cannot be false in mixed characteristic because it combines both sides. And the way to rectify is by the way of the following theorem of myself. So let L be a Neff line bundle. Let L be a Neff line bundle on X, which is projective over an Noetherian scheme S. So the projective scheme X over an Noetherian S. Then L is semi-ample if and only if L restricted the exceptional locus and L restricted to characteristic 0 is semi-ample. So we are just assuming that the char 0 part is valid for this L. But we can often prove it by vanishing theorems or analytic methods. So, and this is the result we use in our mixed characteristic MMP to construct contractions in dimension 3. Similar ideas can be applied to other problems. So for example, similar ideas can be used to show that Collar's results on the existence of quotients by finite equivalence relations extend from positive to mixed characteristic. Can also be used to give new proofs of Kill-Mori theorems on the existence of quotients by reductive group scheme in a mixed characteristic. Now let me tell you about the consecutive theorem, which very strongly builds on the previous one and also builds upon and generalizes very important work in positive characteristic of Kashini Tanaka and Bud Schulze. And so the statement is as follows: let X be a scheme which is proper over an excellent scheme S. Then the Neff-line bundle L is semi-ample if and only if L restricted to characteristic 0 and L restricted to each prime P, and L taken mod every P are semi-ample for every P. The way you apply this theorem is that you reduce your mixed characteristic problem to two independent problems. In characteristic 0, you're just going to apply analytic methods or vanishing theorems. And in characteristic P, you can apply Frobenius methods. The slogan or the mantra behind this theorem is that to construct a morphism in mixed characteristic is enough to do so independently. In positive characteristics and characteristic 0. Another way to think about it is imagine you're trying to construct your final fibration in the minimal model program. Or imagine you're trying to construct a Calabi-Yau fibration in abundance. And you want to do it using polynomials with only integer coefficients. And so this result tells you the following. First, construct it with polynomials with rational or complex coefficients. You are able to use your fractions to your heart's content. Then achieve the same goal, but using congruences modulo P. Then this theorem tells you that you can cook up polynomials with integer coefficients that achieve the same goal. And this result is used in the 4-dimensional minimal model program with Christopher Haken and in the proof of 3-dimensional abundance conjecture by Bernasconi, Brivio, Stignet. Okay, so I know that these last few slides were kind of a lot. There's a lot of technical details, but I hope that kind of some ideas went through. And so I'd like to conclude today's talk and our mini lecture series with a series of applications. And I picked 3 applications for us today. So the first one pertains to the study of the moduli spaces of stable surfaces. Now, Zsolt Patak-Falvi, I think, is gonna say a little bit more about this. So I'm gonna be brief. And so the goal here is to generalize the Lin-Mumford's moduli space of stable curves to higher dimensions in arithmetic settings. And building on the work of Alexeyev, Patak-Falvi, Pozva, Haken, Kovac, BMP, STWW, one can obtain results in this direction. Let's mention 2 of them. So as concluded in the 7-author collaboration, the moduli space M2V bar of stable surfaces of volume V exists as a separated Artin stack with finite diagonal over Z1 over 30. And if you were in Fabio's talk, he already explained that yesterday. He already explained that 30 is the same as 2 times 3 times 5. These are our bad primes. And by the work of Arvidsson, Bernasconi, and Patak-Falvi, assuming semi-stable reduction conjecture for surfaces, you're going to get that this moduli space is in fact proper. So let me review a couple of notions that are used in these results. So first is a stable variety, generalized stable curves to higher dimensions to have both a global and local condition. The global condition is that a canonical divisor is ample, and the local condition is that the singularities are semi-log canonical, which is a natural generalization of nodal singularities. Now, the semi-stable reduction conjecture says the following. If you start with a model over some DVR or a curve, some degeneration, then up to taking a finite cover, a base change under a finite cover of the base, you can assume that there exists, and taking some blowups, you may assume that your model has simple normal crossing and reduced special fiber. This is known in characteristic 0, is a very important tool in characteristic 0, but is vastly open in arithmetic settings beyond dimension 1. Now let me say a few words of how the minimal model program fits into this picture. And as always in the moduli theory, the idea is you're starting with some deformations of surfaces, you're extended to degeneration, and you need to make sure that the special fiber lives on your moduli space. In general, it can be really, really bad. So you can use semi-stable reduction and similar tools to make the special fiber be nice, but it can be highly overcomplicated, may consist of a lot of unnecessary blowups. And then you can run the minimal model program to simplify the special fiber and to make the whole degeneration much nicer. We're going to see a similar phenomenon on the next slide. So now let's move a little bit more towards arithmetic applications, in particular criteria for good reductions. Let R be a local complete DVR of mixed characteristic 0 p greater than 0, and let K be the fraction field of R. A famous theorem of Sir Tate says that we have a way to detect good reductions. So let me recall that a good reduction is a degeneration or a model in which the special fiber is smooth. These are a very nice model. We really like models when the special fiber is smooth. And so this result says the following. If you start with an abelian variety over K, equivalently a deformation of an abelian variety, then you're going to have a good reduction. You're going to have a model with you're going to extend it to a model with smooth fiber. If the Galois group acts on the first étale cohomology in an unramified fashion. So you can detect this conditional good reduction by purely cohomological methods. And this can be extended to other classes of varieties in the framework of Ock-Schaffer-Revisch type conjectures. So here, let me mention the work of Liedtke Matsumoto, which is then extended to all characteristics through the MMP work of Takamatsu and Yoshikawa. So let's start with a K-free surface X. And let's assume this K-free surface X has a semi-stable model. So up to finite extension of the base, we may assume that we have a simple normal crossing and reduced special fiber. Then if the Galois action acting now on the second cohomology is unramified, then X is going to admit a good reduction after maybe some unramified extension of K. There are various statements, related results. There is the original results of Matsumoto, and then the work of Charley-Lotto and Lasda and Liedtke that give many other criterions. In particular, they provide a full good reduction criterion, but then you need to add kind of a more cohomological, you need to assume more things on the cohomological side. Nevertheless, it kind of tells you, and you can imagine these kind of statements are very useful in the study of the generations of K-free surfaces. Now, of course, I have no time really to tell you more about the arithmetic components of this proof. What I want to do today is to tell you how the minimal model program fits into this story. And this is the idea that shows up in many other papers, like, for example, in the works of Davish-Mollick on Artin's conjecture. And the idea is as follows. Using MMP, you can construct nice models of K-free surfaces. Specifically, let's start with a K-free surface X over K. Then up to some finite extension, you can definitely make the special fiber reduced and simple normal crossing by semi-stable reduction, assuming that. But then the relative omega is going to be very, very complicated. It's not going to be trivial at all. If you take any semi-stable model, that you have no ways to say anything about relative omega. However, by running the minimal model program and then using certain results of Artin on simultaneous resolutions of RDP points, you can create a model in which the relative omega is trivial. In other words, you show that up to finite cover, every K-free surface model, every K-free surface, the formation of K-free surface has a model where omega is trivial in total. So it's a very nice kind of like a K3. They really look like K3 models. And so this is the MMP input, and then using these results, you then apply arithmetic methods to study of this problem. Now, you don't really need to assume the semi-stable reduction conjecture in always. There are certain statements that if you have ample line bundles with whose square is relatively smaller than P, then you can construct such semi-stable reductions automatically. There are all these works with Davish-Mollick and others. Okay, so that was the second application. So now let's move to the third application related to the study of the liftability of Calabi-Yau varieties. And so here's the following theorem, originally due to Christopher Haken and myself. We are using four-dimensional mixed characteristic MMP, and because of that, we need to assume resolutions. But there are some new results coming along, the work of Kurama Perry, when they are able to replace some of the parts on the existence of flips, specifically so-called flops, with methods coming from derived categories. And by doing so, they can drop our resolution assumptions and even extend the results to P equal to 5. Unfortunately, these kind of methods do not apply in the singular setting. Okay, so here's the result. Let X and Y be birational Calabi-Yau threefolds of characteristic P greater than 5. Then if X lifts all the way to characteristic 0, not every positive characteristic variety lifts to characteristic 0, it's a kind of a special property of varieties, then Y gonna lift as well. In other words, liftability of Calabi-Yau varieties in dimension 3 is a birational invariant. It would be very nice to give an intrinsic proof of this statement using maybe motivic integration or p-adic integration. But the only proof we have use mixed characteristic MMP. And so the idea is very simple. Let's start with a lift X. Let's call it curly X. X was 3-dimensional, so curly X is a 4-dimensional mixed characteristic variety. Now X and Y, by work of Kawamata extended to these arithmetic settings, are connected by flops. Flops are very similar to flips, but K canonical divisor is trivial for flops. So we have some very complicated birational map between x and y, but these are connected by very simple operations, these flops from xx to x1 to x1 to x2 and so on. And even though it's hard to lift the whole birational map at once, it's much easier to lift flop one by one. And so we are going to use the four-dimensional mixed characteristic MMP to show that these flops lift to a map. So x to x1 is going to lift to a map from curly x to some curly x1 that lifts x1. Then the map from x1 to x2 is going to lift to a map between curly x1 and curly x2. And you're going to keep going until you construct a lift curly xn of xn. But xn is equal to y. And so we get the lift curly xn of y. And we show that y lifts as well. So the idea is, again, it's hard to approach hard problem at once. Just split them into basic subproblems and solve them one by one. And so on that note, let me give you the last slide. So this slide consists of a collection of various problems in which the minimal model program in arithmetic settings, both in positive and mixed characteristic, was applied, in number theory, the study of singularities, models, and other. And there are many more results, but they did not fit on this slide. And I'm very hopeful that in 10 years' time, a lot of young people is going to give talks at a consecutive conference telling us about many, many more of such applications. And on this note, let me conclude my talk today and the joint lecture series with Carl and Kevin. And thank you so much to listening to my talk.
Questions? Comments?
Go back to the previous
This one?
complicated. Can you give an idea of how you list one clock to four-dimensional?
So it's a little bit technical, but the idea more or less is that flop is given by some flopping contraction, and that flopping contraction is detected from the cone of curves, and you're going to see that the same curve is going to lift on the mixed characteristic things, and so the minimal model program is going to force to do something about it. You need to do a little bit of work to say that these curves lift in an appropriate way, and you use some assumptions of singularities. But the kind of idea is you take that curve that you want to flop. This flop still lives in mixed characteristic MMP, and so when you run the MMP appropriately, it forces to flop that curve. And because you're flopping it in mixed characteristic, there's kind of a unique way to do it. So in mod P, it is also going to do the flop you want. So I know this is a little bit oversimplified, but that's kind of the idea.
Can I ask about this semi-analyst?
Mm-hmm.
Did that to check for selection class? Did semi-analyst together with semi-analyst?
Right. So I mean, in theory, yes, in the sense that if you know that it's true in characteristic 0, then by kind of an openness condition, it's going to be true for almost all fibers. So you only need to check a finite number of fibers, but that's not explicit. I think there was some conjecture by Janusz Kolar, who kind of predicted that there's maybe a way to kind of in some situation detect how big primes you need to look at, but as far as I know, this hasn't been established.
Further questions? What slide were you talking about semi-analysts?
This one?
Mm-hmm.
Oh. Okay, now I really don't remember. I definitely needed to use excellent to prove. Yeah, sorry. I mean, usually excellent comes from resolutions of singularity, so maybe I use resolution in characteristic 0. But at this point, this was so many years ago that I do not remember where else could I have used excellence. There's a lot of theorems from Stack's project I've been citing, and then I took the maximum over all the assumptions there.
So anyone can clarify this point?
Is there any known result on lifting programs for funnel recorders?
Yeah, so there's a very new exciting result by Kawakami and by Hiramu Tanaka. I think they established that the smooth three-dimensional funnel varieties all lift to characteristic 0, at least if the characteristic is p greater than 5. I do not remember, but maybe Tatsuro is going to tell us in one of the talks here. Anyway, we know now a lot about smooth three-dimensional funnel varieties. And now the next thing you could ask is about singular funnel varieties. So if we could show that the moduli, if we could show that funnel varieties belong to some bounded family in mixed characteristic over Z, you're going to see that there are there are going to be two types of components of such moduli space. There are going to be the vertical components over special fibers, and there are going to be the horizontal components. And so that generic flatness, you're going to get that funnel, even singular funnel, say epsilon KLT funnels, they're going to all lift to characteristic 0. And that's kind of a thing you might hope for. But to prove such a statement, we would need to establish BAP for three-dimensional varieties. There's been a lot of progress with, I think, Kenta Sato and Prakash Das and others, but it's still the question is open.
Questions?